Hello and welcome to another video. Today we're going to be speaking about a popular mathematics topic, the Riemann hypothesis. This problem hasn't been solved for over 100 years, and the person who solves this problem will receive $1 million as a reward from the Clay Institute. So far, no one has solved it, and we're going to be speaking about the man in charge. The man who first proposed this hypothesis is Bernard Riemann. This is his most recent profile picture from social media sites, and this is his function. This is the function graphed around the point 1/2. I'm going to speak more about this special point of this function, and I'm going to define the function from 1 onwards. So we understand the function, how it behaves if on the interval from 1 to plus infinity. For the understanding of this topic, you're going to need to know complex numbers. I'll make a video on them later. But the whole point of this function is, if I just scroll to the right, so this is the notation for the Riemann zeta function. It's basically a sum of numbers with an exponential value. S can be, well, the function is really defined when S is greater than 1. And we're not only looking at the real number plane, we're also looking at the imaginary number plane. Imaginary axis, sorry. So we're not just focusing on the real numbers this function spits out, but we're also looking at the sort of imaginary component of it, of our output. So we know it's a sum. We can sort of plug in various numbers for S, so let's say like 2, 3, or 4, and we'll get a point somewhere on our plane. We understand how the function behaves. This is not the interesting part of the function. Now, one thing we have found out so far is that the Riemann zeta function at the point -1 converges to -1/12. Again, we're speaking about complex numbers, so this might not make sense at first because it looks like just like usual sum, but actually if we input the value -1, the output value maps back to -1/12, which is somewhere around here. Okay, speaking more of the function, let's have a look what I have written down here. So when do we have zeros? We're going to focus on when we have zeros in this function. So we have found out that all numbers like -2, -4, basically all the negative even numbers are mapped out to the origin, to 0, to this point. So if we plug in -4 into our function, we get the output 0. -2, any even negative number. We call these zeros trivial zeros because we know about them. Now the focus is really on this weird point from 0 to 1. This is where we're going to be focusing. And Riemann stated that all of the zeros that are in this sort of shaded area are around the point 1/2. So if we add, obviously this doesn't make sense if you've never learned about imaginary numbers, but if we have 1/2 plus some value I or minus some value I, it'll sort of move it on the y plane. And all of these values of I map to the origin, which is 0. And we have to prove that. So we have to prove that all non-trivial zeros are at the point 1/2 plus some imaginary component and lie on the orange line. So this line is supposed to be a very straight line, obviously it all goes through 1/2. Now, what we could do is we could just go around the problem. So instead of looking for all the zeros on this line, which goes into infinity, all we have to do is find a zero that is not on this line. So for, let's say, some values like 1/4 or some smaller or larger or greater values than 1/2 lying in this in this area. So from 0 to 1/2 and from 1/2 to 1. If we find 1 0, that disproves the statement because he said that all the zeros lie on this part of our plane. And if we disprove that, we win basically a hefty sum of $1 million from the Clay Institute. So, I hope you liked this video. Please make sure to like, comment, subscribe, and share. And if you have any comments on the topic, or if you feel like you've proved the Riemann hypothesis, which most people will definitely say just to get this hefty sum of money, then comment down below and tell me what would you like to see next. Thanks for watching.